Good morning, everybody. Today we're going to finish looking at normal force. So an important idea about normal force that we have not yet talked about is the fact that normal force actually also goes by another name when in relation to a person. Okay? Normal force is also called apparent weight. Now, if you'll think about the term apparent, apparent means seems like or acts like. So apparent weight seems like your weight, but it's not. Now, why is it called this? It's called this is because normal force, not gravity, is what gives us our sense of heaviness. We cannot actually feel the pull of Earth acting on us. That's why when you're in free fall, when the only force acting on you is gravity, you feel weightless. Now, does that mean you have no weight? Of course not. Gravity's acting on you. You're in free fall. But since you can't feel Earth's pull acting on you, you feel like you're weightless. There's nothing to give you a sense of heaviness. There's no normal force in free fall. So the normal force acting up on you from a surface is called your apparent weight because that's what gives you your sense of heaviness, your sense of weight. Now, it's not your true weight, so that means it can change value because your gravity, your weight from Earth, always stays constant when it's acting on you, okay? But normal force can change value. And that's what we're going to be looking at today. So let's take a look at apparent weight of a person and how it can change relative to your true weight. Okay, so we're going to look at this example, number 7. I want to introduce everybody to George. George is my buddy who stands in the elevator. I don't know if you remember this, but decades ago, when big, tall buildings had elevators and people would go to work or go shopping in these big, tall buildings, there would be a person in the elevator to open and shut the door and push the button for you to go to your floor. Well, that's George's job. So George is in our elevator, and George has a mass of 45 kilograms. Now, we want to know what is George's apparent weight. What is the normal force acting on him from the floor of the elevator in 3 different situations? First, when the elevator is moving up at constant speed. Then, when it's moving up with an acceleration. And when it's moving down with an acceleration. Okay, because in each of those cases, the normal force is not necessarily the same as your true weight, which means what you feel will be different. Okay, so let's start by simply taking our paper and let's mark it off into 3 sections here, 1 for each part. Okay, that gives us plenty of room. All right, we're going to start with part A first. Now this is when George and the elevator are moving up at constant speed. Now, we know something about an elevator at constant speed or constant velocity. That means you are in equilibrium. And when you're in equilibrium, that means all the forces balance out. The net force must be 0 so that there's nothing to change the motion from constant speed to something else. Okay, let's do a free body diagram real quick. So here's George, and we want to look at the forces acting on George. We know we have George's true weight acting on him from Earth, his gravity, and we have the normal force acting on him from the floor of the elevator. Now, nothing else is acting on George except the floor of the elevator, okay? The cable that acts on the elevator is not touching George, so we don't look at that. It's touching the elevator. The only thing making George go up is the elevator floor. Now, because we're in equilibrium, we know that the normal force acting on George from the elevator floor must be equal in value to George's true weight because of equilibrium, okay? So that means we can set the normal force equal to the true weight, and if we say 45 kilograms, George's mass, times the acceleration due to gravity, then the normal force as well as George's true weight must have a value of 441 newtons. And that would be upward, okay? That would be upward. In fact, we could go ahead and say up is the positive direction. That's what we'll do in this problem. We'll take up to be positive and down to be negative, okay? So this is positive 441 newtons. And that is not only the value, the magnitude of George's true weight, that's also the normal force. So what does he feel? All right, George feels his usual heaviness. He feels like he normally does if he's just sitting in a chair somewhere. Okay? Now, the situation is going to change next, however, because now George is moving up with the elevator with an acceleration of 0.5 meters per second. So let's take a look. Part B, George has an acceleration of positive, because that's upward, 0.5 meters per second. So now we're in a state of non-equilibrium. Not everything balances out, in other words. There's something left over that makes George's mass accelerate, and that would be the net force. Something left over when you add the forces. So let's first look at a free body diagram of this situation. Now, George still has his true weight. That hasn't changed. It's the same as it was before, okay? Same as it was before. But now, in order to accelerate up, to change velocity as you go upward, the normal force must be larger than George's true weight. Okay? And we're still going to let up be positive and down be negative. So the normal force must have a value greater than mg in order to accelerate up. So let's see. We're going to be using Newton's second law now. All right, we know the sum of the forces, that's what the net force is, makes George's mass accelerate. Now, what forces and what directions do we have? We've got two forces in the sum. So we've got the positive normal force, magnitude, direction, plus we've got the weight, magnitude and direction, negative direction. The acceleration is also a vector, and it's positive. Always stick in the signs for your directions when you write your formula. Okay? Now, let's do a little algebra. In order to solve for the normal force, we need to take this to the other side, so that makes it positive. So we get N equals MA minus MG. All right? So the net force minus the weight tells us how much normal force, oh, not minus, plus, because it was negative over here. Sorry about that, guys. Make that a plus. It was negative over here, so it's positive over there. So we get 45 kilograms times 0.5 meters per second squared plus, now we already found George's true weight over here, so I'm just going to put that in instead of writing out the mg. Okay? So we get 441 newtons of weight plus the net force. So the normal force then would have to have a value of 463.5 newtons. Notice it has to be bigger than the true weight, so that what's left over makes the mass accelerate. Okay? In fact, it looks like it's about 22 newtons, 22 and a half newtons left over, and that makes George's mass accelerate. Okay? Now, how does George feel when the elevator is accelerating up? George will feel heavier because His apparent weight, what gives him his sense of heaviness, is greater than his true weight. He can't feel this. This is what gives him his sense of heaviness. It's bigger than it usually is, so he feels heavier. Whenever you accelerate up, whether it's in a roller coaster or an elevator or an escalator or a plane, whenever you accelerate up, you feel heavier than you usually do. Now let's look at the last case. This is when the elevator's also got an acceleration of 0.5 meters per second squared, but now moving downward. So let's take a look. All right, the acceleration equals positive. No, not positive. The acceleration is downward. So that's negative 0.5 meters per second squared. And because there is an acceleration, that means we're in a state of non-equilibrium, which means we'll be using Newton's second law. Okay? Be focusing on that a little more. All right. So, new free body diagram. Here's George's true weight. Hasn't changed one little bit. But in order to accelerate downward, this has to be the bigger force now. Okay, this has to be the bigger force. So that means the normal force now is actually smaller than the true weight. All right, so N must be less than mg. And we're still going to let up be positive and down be negative. All right, we're also going to continue to use Newton's second law here. The sum of the forces, or the net force, makes the mass accelerate. We've got the normal force pointing up. We've got the gravity pointing down. We've also got the acceleration, which points down. So guys, that's going to be negative ma. All right, I'm taking that negative and sticking it right there because it is a vector and it points down, and down is negative. All vectors must have the appropriate signs for our sign convention. So there we go. This is one that people tend to forget a lot. They look at these two because they're right there on the free body diagram, but they forget this is a vector as well. You can't do that. You've got to remember that must obey the sign convention also. All right, so now when we do our algebra, add this to the other side, we get negative ma plus mg. So you're going to end up saying negative 45 kilograms times 0.5 meters per second squared plus 441 newtons, George's true weight. And now you end up subtracting these two instead of adding because of that negative. You end up with a value that's smaller than 441. In fact, it's 418.5 newtons. If you wanted to round to 419, that's okay. All right, so now George's apparent weight is less than the true weight. So how does George feel? He feels lighter. Anytime you accelerate downward, whether it's in a roller coaster down the first big hill, or in an airplane that's doing a dive, or in an elevator or an escalator, anytime you accelerate down, you're going to feel lighter than you normally do, lighter than you usually do, lighter than your true weight. In fact, if you're in free fall, you won't feel any weight at all. You'll feel weightless because the only force acting on you is gravity and you can't feel it. Okay? So you would feel weightless. All right, so normal force in relation to a person is also called apparent weight, or seems like weight, because that's what gives us our sense of heaviness. And because it can change value, how heavy we feel can also change value, even though our weight itself, our true weight, always stays the same. Okay? Kind of an interesting idea, isn't it? All right. Thanks for listening. Bye-bye.